Welcome to this lecture on part of power quality on passive shunt and series compensators. I mean this passive shunt and series compensator are normally used only in when you have a sinusoidal supply voltage. So, we like to of course talk about the today presentation, the introduction, then the state of art on passive shunt and series compensator. We will classify these passive and shunt series compensator. We will talk about the principle of operation of passive shunt and series compensator. We will have analysis as well as design of passive series compensator with the then followed by numerical examples and summary and with the references with that. So, very objective of this today presentation is the requirement and application of lossless passive compensators. We will talk about the configuration of passive shunt compensator and we like to analyze and design of this passive compensator. We will of course have a modeling and performance of this passive compensator and certainly we will have a potential and limitations of passive compensator like. Well, to introduce this passive compensator consists of lossless reactive elements such as capacitors and inductor with and without switching devices, and they can supply or absorb variable or fixed reactive power locally to meet the requirement of these power quality problem and improve the power quality of the power system by enhancing the efficiency and utilization of equipment in transmission and distribution network. And this consists mainly with, as we really show the photo here. So, this consists of your different inductors, kind of reactors as well as the capacitors which you AC capacitors you can call it, because it is a AC network. So, this kind of compensation we are talking about when we have a sinusoidal supply voltage, okay, and we have a like a sinusoidal supply current, but certainly we might have a problem of your typically of reduced voltage, or we might have a reactive power problem, we might have a load unbalance if it is a typically of your 3-wire system and 4-wire system, we might have a even the neutral current because of unbalanced load also. So, we will be talking about in this such a linear environment only the typically compensation by the lossless component, basically the inductor and capacitor. So, they store energy in one half cycle and relieve energy and they complement to each other, but I mean like we consider that there is no, you can call it like harmonics and other things in part of the system. So, these passive compensators are used in transmission system typically for improving the different like say performance, like they improve the voltage profile, then improve the tangent stability. They are also used to improve the steady state stability, dynamic stability, voltage stability, angular stability, and of course, the losses reduction by providing the compensation of reactive power, enhancing the load ability and improving the transmission capacity of the transmission network and damping the power system oscillations and mitigating subsynchronous resonance and other contingency problems. And normally you can clearly see in this photograph the capacitor banks of very large rating shunt compensator bank for power factor correction and series and shunt compensator bank for transmission system, like providing the compensation transmission line at the substation and in series with the line. The passive compensators are extensively used in distribution system for improving the voltage profile at the point of common coupling and of course, for losses reduction, the power factor correction, providing the load balancing and providing a neutral current compensation and for better utilization of distribution equipment like Well, you can see clearly the photograph how the capacitor static VR compensator look like and how the high voltage parallel capacitor compensator look like also. Then the like a reactive power compensation system, the photograph on the left side and right side you can see air core series and shunt reactors like which are used in very high voltage network like on transmission system. Well, you can see the high voltage, some high voltage substation contains large air core reactors. A reactor in the context is just by large coil. These can be used as a part of static VR compensator, and this is the way of adding either capacitance or inductance to the electricity system depending on which is needed, and air core reactors provide the inductance. They can also use as filters to filter or unwanted frequencies in the system. Well, this is typically a power compensation device electrified on railway series capacitors device at typically 44 kV and 3.6 MVAR just like as an example to give you confidence. We would like to of course talk about state of the art on this passive shunt and series compensator. Well, the passive compensation is now mature technology for providing compensation for the reactive power for power factor correction and or voltage regulation, but these two cannot go simultaneously. Either you might be using this shunt compensator for power factor correction or voltage regulation. Then it can be used for load balancing and reduction of neutral current in AC network. So, this is basically for the, you can call it for distribution system. These passive compensators are also used to regulate the terminal voltage, to suppress the voltage flicker and to improve the voltage balance and power factor correction and load balancing and neutral current mitigation in 3-phase distribution system like. Well, in early 20th century, Siemens has investigated that an unbalanced single phase resistive load may be realized as a balanced load using lossless passive element on 3-phase supply system, and this concept later on extended in many directions such as balancing of 3-phase unbalanced loads, power factor correction at supply system, negative sequence and zero sequence current compensation and voltage regulation. Since these compensators are simple, cost effective and easily realizable in practice, so they are still used in large power rating. We would like to classify these passive shunt and series compensators. Well, we classified based on the topology, like either they are connected in shunt or series or combination of both, like as a hybrid, means you have a series compensation as well as shunt compensation. It also can be classified based on number of phases. I mean, you are using this compensator either in 2-wire system like a single phase system, or you are using this in 3-wire and 3-phase system, or 4-wire 3-phase system. So, that is another classification of these passive compensator you can have. Another classification is the topology based compensator, that we already talk about shunt, series and a combination of both. And then typically if we talk about first for series compensator, it is used to eliminate voltage sag, swell and fluctuations, and series passive compensator have a limited applications in distribution system as they affect the performance of the load to great extent and have resonance problem. And the series passive compensator are used in transmission system to improve the power transfer capability of course, with the restricted capacity to avoid the your series resonance. And these series passive shunt compensator are also used in standalone self-excited induction generator to improve the voltage profile, enhancing the stability. Means you have a here the series compensator, I mean you have a source impedance or feeder impedance, and then you have a series compensator followed by the load. So, normally it is not used in, typically you can call it in the distribution system, it is preferred to in transmission system, because presence of this will affect the voltage across the load, like I mean also. Well, the shunt passive compensator normally connected in shunt with the load at the closer to the load. So, it used to regulate the voltage across the load or the power factor using reactive power. So, you can provide by the help of this the reactive power of the load, and so that here at the supply side you have a power factor unity, and these are also called static wear generator in the power system network for stabilizing and improving the voltage profile. So, virtually when you are not drawing the typically the reactive power from this, the voltage profile also improve. But you can, I already mentioned earlier that either you can improve the voltage profile or you can do the power factor correction, both you cannot. Little improvement in voltage profile is always there with the unity power factor, but you cannot of course, I mean both simultaneously, either you can regulate the voltage or you can regulate typically the correct the power factor like. Well, this is the typical case of hybrid compensator. They are used in standalone self-excited generator to improve the voltage profile, enhancing typically. So, you can just see as a typically a compensator in series and then in parallel, and another compensator here in series with the line and parallel with this. So, this we call it typically a short shunt, and this we call it a kind of long shunt, like long shunt in the sense that series is put typically in this. So, both the configuration I mean have been used in self-excited induction generator for regulating the voltage across the load also. Well, the classification which we are talking about, another classification on supply system, it classified into 3 categories, like a 2-wire single phase system, 3-wire 3-phase system and 4-wire 3-phase system. Well, taking a first case of 2-wire passive shunt compensator. So, 2-wire single phase passive compensator are used in all 3 modes as series, shunt or combination of both. And here if you look into the like a shunt compensation, I mean if we connect this typically a compensator which is here, it is shown in parallel with the load, and well you can decide the design of this for the all 3 purpose, like if you can call it like a typically like maybe a power factor correction at load end, and if you correct the power factor at load end, the supply current, this current should come in phase. So, whatever the reactive power of the load is required, that you have to compensate with the this compensator like So, this is the power factor correction at the load end. The another compensation can be power factor correction at substation, means you can correct the power factor at this point virtually, and that is the in that case like the supply current should be in phase with the supply voltage. Here the supply current is in the phase with the load voltage, here is the supply current in phase with the supply voltage. It means you are correcting power factor here, and you will require little higher value of the compensator. So, that power factor correction is here not there, it means virtually you have to compensate even the series impedance of the load also like. So, that is the meaning of this, and this is the phasor corresponding to that like. The third is the 0 voltage regulation, which we were mentioning. So, you are putting a compensator here, that the voltage here, whatever the voltage is at no load, when load is not connected, this voltage gets reflected here, and when you put the load, this voltage will certainly deviate depending upon the power factor of the load. It may go down, lagging power factor will be down, and with the leading power factor it will go up. So, you have to put a compensator in parallel to that, and this voltage will be equal to the supply voltage. That is also possible, as you can see the phasor diagram here. We have a load voltage, we have a load current, and now you are with the help of this compensator virtually you are making this supply current little leading with the typically from the your leading from the load voltage, and then you have a drop of feeder impedance, resistance and the reactance, and this is the voltage. And of course, if you take on the same circle, it means the magnitude of Vs equal to Vl, it means you got the your 0 voltage regulation, means whatever the voltage is at the load end is the same supply voltage, it means your no load voltage will become the full load voltage. So, this is the condition. So, you can consider out of 3 conditions only one condition can exist, and this gives the certainly a design corresponding to the substation, that how much the compensator we should put, so that voltage profile can be improved at the substation station itself like. And this is of course, the normally this condition is at the substation, this condition preferred by the industry of individual industry in their premises, because they are otherwise penalized for typically for poor power factor penalty like. So, this avoids the poor power factor penalty, and this gives the real design of how much this should be the value of compensator component like. If we talk about like a 3 phase star connected load, usually you have a, if you have a like a typically a maybe unbalanced load or balanced load on 3 phase 3 wire system. So, here is a typically a point of common coupling, and you have a connected 3 phase star connected load. Load can be star connected or it can be like a delta connected. So, if we consider this load is equivalent to a star connected load with isolated neutral, this neutral is not connected with the supply neutral, that is the one case. So, you will have a different cases in case of 3 phase system possible, and this is in this case of course, this load can be you can call it this load of your star can be converted equivalent to delta, or you can have a delta connected load across the 3 wires. So, both the cases can be converted into this equivalent to this here. Either we have a delta connected load like which we have a delta, we are connecting here the admittances of the load, or you might be convert from the previous case which was a star connected, you can convert equivalent to delta connection, which you could have studied even at the first year engineering course to convert delta to star to delta conversion. So, you got 3, and which are the unbalanced admittances, or you can call it unbalanced load. Now, you can keep a 3 compensator parallel to it, and these compensator can provide the different functions like. So, if you provide this compensation only for typically kind of reactive power of individual load, here this network can be converted equivalent to here 3 your conductances typically of 3 conductors, but it will be your can be of unequal value, because this may be load may be unbalanced. But what we are doing by this compensator putting a like VCAP, just only reactive power or reactive power of the load we are compensating by putting a shunt compensator here, shunt compensator here, shunt compensator here, similar to what we discussed already in the case of single phase. So, this can be made equivalent to a your let us say conductance here, typically here also, here also. So, this become you can call it a pure resistive load, unbalanced pure resistive load. So, this can be converted by this set of compensator, and this compensator we call it for the purpose like we are putting like a P component, we are mentioning here as a because we are putting across AB line, BC line, CA line. So, that is represent for that, and P for providing only power factor correction here like that is the meaning of the P notation put it here, and this can be converted to this unbalanced delta equivalent connected unity power factor load like or so. So now we can put another set of compensator, okay, here typically where we are connecting this compensator for providing the balancing. I mean balancing in the sense that there is a I mean the what Stevens has given that even a single phase load can be realized as balanced load, means any unbalanced load which is like a resistive load, these three resistive unbalanced load, by putting a compensator, this three phase load can be realized here on this system as a balanced load and resistive load. So, this can be represented equivalent to here, that equivalent to a delta connected, okay, resistive load with the conductance of GD all equal as a balanced load. So, it means lossless compensator means capacitor and reactor can provide your power factor correction, making them resistive load and then equalizing them or balancing the load. So, then you will have a three phase balance current flowing into the supply system at unity power factor, because equivalent it is equivalent to a kind of resistive load like also. And well, this now that kind of situation can be converted to equivalent. I mean that was delta connection. So, you have to convert into star equivalent, okay. That GD you have to convert equivalent to star, and that is GY, okay. Here now in parallel to this you can put another compensator on per phase basis, which can either do typically here the voltage regulation also. For power factor correction we did there for balance, but if you want for voltage regulation, then certainly you have to put another compensator for regulating the voltage across this and converting. So, this is same as equivalent to single phase what we did earlier in the first case, and then putting a compensator for regulating the voltage across there. So, now we have a kind of three set of compensator, one was for power factor correction for individual phases, another was for load balancing, okay, typically with making a equivalent to a resistive load, and then now for voltage regulation we have to convert equivalent to star connection and put this another compensator for regulating the voltage, load voltage equal to the phase voltage, as we discussed in case of single phase compensation like also. Well, that was the three phase 3 wire system. Now, coming to 3 phase 4 wire system. I mean 3 phase 4 wire system means you have a neutral also, and you have a 3 phase 3 unbalanced load with the neutral return. That is the original system, you can call it A phase load, B phase load, C phase load, and connected between neutral of supply and this, and there is a possibility that these load of course can be unequal, unbalanced, even one can be, even there may not be any load, even one phase or two phase, only single phase load may be there. So, lot of conditions can be there, or it can be all three unbalanced load like. So, now a large number of single phase load may be supplied from 3 phase AC means with the neutral conductor, where neutral current conductor is connected here, and they have been developed as shunt, series and hybrid with the series and shunt compensators. So, for this purpose, I mean you can understand this typically, I mean now what we need a compensator, we need a 6 branch of the compensator. Why we require the kind of 6 branch? I mean equivalent to, first we can make this a one compensator here to make a kind of like making a power factor correction of individually. Okay. Once you correct the power factor individually and compensating the neutral current also, then it becomes neutral current. If it is 0, then it is like a star equivalent, which you can convert into delta equivalent, and you have a delta compensator to make a balancing of this network like also. So, here you have a like a kind of 6 element also, but you will find very interesting observation here, which I will discuss probably with the next slide here. So, which can be converted equivalent to like a again star equivalent per phase, and then it for voltage regulation you can put compensator similar to like what we discussed in single phase like. So, you might have plenty of cases in 3 phase 4 wire system, and finally coming to this like also. So, we will talk about principle of operation of this passive shunt and series compensators. So, the main objective of passive shunt compensator are to provide reactive power compensation for linear AC loads for improving the voltage profile, even for 0 voltage regulation or power factor correction, both cannot go simultaneously. So, in 3 phase 3 wire circuits, the 3 passive shunt compensators are also provide load balancing at AC means in addition to the 0 voltage regulation or power factor correction like. So, in 3 phase 4 wire circuit, these passive shunt compensators also provide neutral current mitigation at AC means in addition to load balancing or 0 voltage or power factor correction. So, nowadays these passive shunt compensators are also used in distributed standalone or renewable power generating system. So, it requires the application of those, because you would like to have a neutral current compensation as well as so that the rating of your typically of your reactive power, I mean these sources are not typically loaded because of the your reactive power or so. and they should not have any negative sequence current or unbalanced current also into that. So, these passive compensator are also used in series configuration and combination of shunt and series configuration depending upon the application and their effectiveness like. So, passive series compensator are used for voltage regulation and enhancing the power flow control in large power system transmission systems, and however, the passive series compensator have much severe resonance problem than the passive shunt compensators, and therefore, they are used cautiously and up to a certain point of compensation to avoid such devastating resonance problems like. In hybrid configuration, these series elements are used with shunt element in some applications such as standalone self-acted inductor, which I already talk about typically. So, coming to analysis and design of this passive shunt compensator, we like to discuss analysis design of single phase passive shunt compensator, then we will go analysis and design of 3 phase 3 wire passive shunt compensator, and we will go to like analysis design of 3 phase 4 wire shunt compensator. So, coming to first case of single phase analysis and design of single phase passive shunt compensator. So, taking an example of a single phase load of an impedance ZL equal to RL minus JXL with this admittance equal to YL 1 upon ZL, and that is GL plus JBL fed from a AC voltage of VL RMS, all these are RMS quantity, and because it is a sinusoidal case like the current drawn by the load is your IL equal to VL upon ZL or VL equal to YL or VL GL plus J VL BL, or that can be equivalent to like your resistive equivalent current active component current plus the reactive component of current like and you can clearly see here like typically the kind of here the with the load current here you have a load current, you have a load voltage, okay, and you have a compensator. So, this is for power factor correction, typically power factor correction at the load terminal, that is the reason that the current typically here in phase with the load voltage, and for this purpose you have to provide certainly the reactive power by this compensator of equivalent to of the load. So, this how much is the reactive component here, this has to be equivalent to capacitive component, and that causes certainly the typically the source impedance drop, resistance drop, because current supply current is in phase with the voltage and quadrature exactly 90 degree leading the inductance source impedance drop like. So, this is the typically you can say phasor diagram corresponding to the power factor correction at the load end, and this is the case corresponding to power factor correction at the substation. In substation means the supply current, this supply current is in phase with the Vs. So, that is also possible in a sense that we have to have a load voltage, that is the load current, we have to provide compensator current here just to compensate that, and then we have a typically the resistance drop and then the minus this reactance drop which comes to equivalent to load voltage like So, this condition you will find you need the little more reactive power corresponding to that like here. So, the apparent power of the load is as like SL equal to VL into IL conjugate, and you can write equal to VL square GL, that is like a conductive part or resistance part of power active power loss, and that is another minus J VL square BL, that is reactive power of the load, and it can be written as JPL plus JQL. So, for large reactive power loads BL and IX are negative and reactive power is positive. So, as the convention shown in the phasor diagram of previous figure, and the load current drawn from the supply is higher than the current to do the actual work IR. So, by a factor of IR upon IL, that is nothing but power factor like in this circuit. So, basic objective power factor correction or improvement in the power factor improvement is to compensate for this reactive power to provide it locally by connecting a compensator in parallel to the consumer load and to reduce the supply current to IR. So, that is the virtually you can call it IS, then in that case will be if power factor maintain unity, IS will be equal to IR, or you can call it that will be IS plus IC, and you found this you can find out the typical value what should be the value of your IC. So, the net result comes only the VL IL, and these two have to be equal and cancel out each other. So, final your current will be VL GL like also only resistive current like. So, by using that compensator in parallel to load with an admittance for power factor correction is equal to YL, YC equal to minus JBL, and after the compensation supply current is minimum in phase with the load or supply voltage, and the compensator current will be your IC equal to VL into YC, or that is equal to minus JBL into VL. The apparent power rating of the compensator is your SC equal to PC plus JQC, and we say VL IC, and there is no active component current or loss in the compensator. So, we call it lossless element we are using like either inductive or capacitive nature. So, it will become J VL square BL. So, this is the kind of a rating VA rating you can call it of the compensator, which is equivalent to VAR. It means that the compensator does not need any active power. So, PC equal to 0. So, SC equal to QC equal to VL square BL minus QL like also. Well, so another case which we discussed it at the unity power factor at the substation feeder for the high energy efficiency, and in this case the distribution feeders and the loads are we form the substation as a pure resistive load, means we look into here as a pure resistive load and putting the compensator. The additional susceptance of the compensator BC is estimated as follows: the imaginary part of the impedance V at substation must be 0 here, like the imaginary part of this must be equivalent to 0. So, from that you can find out what is the imaginary part of this total impedance RS plus JXN, and in parallel these two elements, like you can keep it here, and from this you can put imaginary part of this, and therefore, the total substance of the compensator is given it BT equal to BC plus BL. BL was for power factor correction and BC is the additional one. So, when we solve this equation, typically we get the BT equal to 1 plus minus under root 1 minus 4 XC square into GL square upon 2 XS. So, by connecting a BT, a unity power factor may be maintained at the substation, and this value certainly will be little larger than what you have a BL like also. So, unless in design for shunt compensator for 0 voltage regulation, that is the another condition. So, shunt compensator for 0 voltage regulation has the following advantage: avoiding the voltage swell caused by the capacitor switching, reducing the voltage sag due to the common feeder faults, controlling the voltage fluctuations caused by customer load variation, and reducing the frequency of mechanical switching operations in tap changing, load tap changing transformers and mechanically switched capacitors for drastic reduction in their maintenance, and enhancing the loadability of the system, especially for improving the stability of the load such as induction motor under the major disturbances. So, these are the benefit of this shunt compensator for 0 voltage regulation like also. That is the reason we have to go for this like, and in substation we use really this panels, capacitor panel for like, and the phasor diagram corresponding to the 0 voltage regulation, which we already discussed earlier also, that you are putting a compensator in parallel with the load, and we consider that this VL equal to VS. So, that is only possible than VL, and if we put like a compensator current little higher, not only the equivalent to load, but we compensate in a manner that the IS and RS drop, we draw a circle with the radius of VL over the center point, and and virtually this drop, this IS will go with this drop, and this drop once becomes typically comes on this circle. So, this becomes Vs. So, in this case Vs will be equal to VL, or you can call it, because we are regulating the here the value of VL. So, VL will change, not the Vs. Vs is constant. So, VL will be accordingly changing and coming on this arc of this like So, that is possible. For this here we will need little more reactive power compared to the power factor correction, because we have to compensate the drop of impedance. At unity power factor we are not compensating the drop of the source impedance, we are making this current in phase with the voltage only, but we are not touching the voltage. Voltage profile may improve little bit, but here we are making sure that voltage is regulated, this voltage load voltage is regulated to the supply voltage by putting some extra compensation here, and that compensation of course, how much it should be there, then this is the derivation of this we can calculate. The additional susceptance of compensator BC for 0 voltage regulation at load terminal is estimated as follows: the total load terminal voltage must be same as the AC voltage. So, Vs amplitude should be equal to VL, and you can find out the amplitude of the typically the VL in terms of Vs. This is with the typically in terms of the VL we found the typically Vs equal to, so we calculate the VL in terms of Vs by putting all the parameters of this compensator load as well as the line corresponding to this equivalent, and this comes equivalent to this. Thus, the total susceptance of the compensator BT is estimated from this relation equal to BT VCV. Why we are saying BCV? Compensator for voltage regulation V plus BL. That is the compensator for typically compensating only the load reactive power, and this comes equal to XS plus minus under root XS square plus minus of A into bracket 2 RS GL plus A GL square in bracket divided by A, where A is nothing but the you can call it magnitude of the source impedance RA square XS square. So, this will make this voltage equivalent to this like from this equation you can typically derive it, you can keep it equal to 0 and then you can find out the root of this corresponding to the value of B t from here, because B t is only in this relation B t is unknown. So, once you will keep equal to 0, then you can find out this root from there. So, by compensating this B t at the load terminal, its terminal voltage V L equal to be regulated the same as the AC mains voltage like. So, that is about voltage regulation power factor correction virtually in case of single phase. Now, we will go into analysis and design of 3-phase 3-wire compensators. So, we talk about analysis and design of shunt compensator for power factor correction. So, any 3-phase unbalanced ungrounded star connected load which is shown in figure below, figure A, may be transformed to 3-phase unbalanced delta connected load by star delta transformation of equivalent by this using this transformation. But this neutral is not connected here. So, this is the isolated neutral. So, this can be converted this unbalanced 3-phase load of star connected equivalent to a delta connected, which you can call it YCA, YBA, YCA, and we can find out from these 3 relations which you could have studied virtually in BTech first year course conversion from star to delta conversion. So, we get admittances of equivalent typically of your delta equivalent of this, I mean from impedances, and this comes in terms of, we call it, this is ZAN, ZBN, ZCN. We put the value of this and we can easily get from there like. And now, we can put the different compensator for power factor correction, which we already earlier talked about with the figure here in this delta connected load, only for individual power factor correction of YCA, then YAB, YBC, also by putting this the different, you can call it the this compensator reactances also. So, the 3-phase delta connected unbalanced reactive load can be defined in terms of admittance, impedance, conductance and susceptances. This is what we have the relation VAB, YAB upon ZAB, I mean all 3 phases we can define. So, imaginary part of these admittances of 3-phase delta connected unbalanced reactive load are to be estimated to compensate the reactive part of them for power factor correction. So, VAPB will be just imaginary part of your A phase, means virtually this part. Similarly, for this B phase, similarly for CA phase like coming. So, it comes like for power factor correction we got these values, I mean like. So, after connecting these compensating component in parallel to the 3-phase delta connected unbalanced load, the resulting delta connected load shown in figure becomes the unbalanced resistive load with the unequal conductances of GAB, GBC and GCA. But now, it becomes a kind of a resistive network of unbalanced load, which is equivalent to here you can see in this figure that we have a, all the 3 conductance like equivalent to a resistive load, but unbalanced load on 3-phase 3-wire system. Like, so this now we can put another set of compensator here in parallel to these 3 conductances, which is responsible for load balancing of this your delta connected load like your 3 compensator, and this equivalent can be realized equivalent to 3 balance delta connected conductances here, as a you can call resistive load, which draws the all equal current, balance current at unity power factor current from this delta typically, or this delta equivalent balance load. Now, it is only important that we have to find out these components like So, the unbalanced delta connected resistive load, which is in this figure, may be realized by balanced delta connected resistive load by connecting 3 lossless passive element susceptances across them, and the value of these susceptances may be estimated using symmetrical component theory given here. The unbalanced delta connected resistive load in figure typically this is fed from balanced 3-phase 3-wire system. So, this is the supply voltage, we have a balanced supply voltage which is equivalent to with the different operator, and now we can say this line voltage we can find out from phase voltage, and this is equivalent to the RMS value of equal to V, and the line voltage are now you can estimate for all 3 phases. They are just 120 degree apart, but magnitude is the same because it is a balanced voltage, and line voltage will be now equal to root 3 times phase voltage and the RMS, where the your Vp is the phase RMS voltage, and 3-phase load current in 3 branches of delta loop will be now, you can call it equivalent to resistor load will be a conductance across the line to line and the line voltage, and similarly for BC and CA. So, these are the current typically of 3 you can call it delta connected current going through those equivalent shunt branches. So, these line current of unbalanced delta connected resistor are as follows. We can find out this typically going to be a current equivalent to IA equal to the line current we can say of difference of the both in terms of the parameters we can find out in this manner, and then we can derive for even the for B line and C line from there, and we can say symmetrical component of these line current of unbalanced delta connected resistor load are equivalent to IO equal to IB plus IG, and I1 zero sequence current from that line current, and then positive sequence current and negative sequence current. And we can say for balanced network zero sequence current should be 0, okay, and the positive sequence current only should be there, and this is positive sequence current and this is the negative sequence current like So, similarly, symmetrical component of the line current of delta connected resistive lossless element must be base compensator must be used for balancing the susceptances, and from there, from comparing these two relations, we can find out that zero sequence of compensate, because you do not have a current of zero sequence, because it is a 3 wire system. So, you have this value typically 0, but the compensator for this I1 you must have the just compensating equivalent to the compensator current should be equivalent to this, and for negative sequence compensator current should be equivalent to this like. So, it means you are taking all the reactive part of it like now resistive part it here. So, that is correspond to your compensator positive sequence current and negative sequence current, and zero sequence is 0 here, because zero sequence cannot flow in this case. So, these negative sequence current of symmetrical component of the compensator and load must cancel each other for load balancing of AC mains, and results the following relation. So, I2 plus I2C must be equal to 0, means negative sequence current of the load should be compensated by the compensator, and these sum of these two should be equal to 0. So, by putting the value of your typically I2 and compensator here, in terms of voltage 0, so voltage goes out. So, you can find out a relation between these two side of quantity. So, these are the load admittances conductances, and these are the typically your susceptances of the compensator. So, you got typically a kind of relation between the two, one relation, and moreover the positive sequence current of symmetrical component compensator I1C must be 0 for power factor correction and load balancing. So, it means I1C also here must be 0, and it results in the relation among susceptances of this compensator typically VABB for balancing VBBC and VC should be 0. So, from there of course, you can find out the value solving those two equations. A set of susceptance may be estimated for load balancing and power factor correction at 3 phase AC main as like VABB in terms of those unbalanced conductances. So, you can find out the compensator for AB, BC and CA in terms of these conductances, and once you get this value, it means the network is balanced equivalent to, and you will get the balance line current equal to Vp into the conducts 3 sum of conductances like or so, and that you can see that is equivalent to G kind of GD. So, 3 phase total 3 phase susceptances to be connected across the 3 lines of AC mains for power factor correction and load balancing of 3 phase delta connected unbalanced reactive load, and now you can find out total conductances of compensator, which is for power factor correction of individual and this balancing for similarly for CA, similarly for BC, for these are for power factor correction, this is for load balancing. So, this comes the compensator what you are connecting the in typically in parallel for all 3 lines or so. So, therefore, by connecting these susceptances VABC, VCC, VCAC and VBC across the 3 line of AC mains, any unbalanced delta connected load may be realized as equivalent to a balanced delta connected unity power factor load, and the parameter of equivalent balanced delta connected unity power factor load are equal to GD equal to 1 upon RD, and which is sum of the 3 conductances V GAB, GBCA and GBC by 3. So, these parameters of equivalent balanced star connected load can be find out GY upon 1 3 into 3 equal to 3D. This is delta to star conversion. In case of delta, you can call it the here the typically in a star the conductance is typically 3 times, but the impedance will be kind of 1/3. So, that is GAB plus GC and G sum of this you can find out, and total power consumed you can find out V square GD, that is nothing but 3 Vp square phase voltage and is equivalent to star conductance here like. So, that is the total power consumed by the load, because all compensator are not consuming, we are considering it is all lossless compensator or so. So, that makes the power factor load balancing and power factor correction of that either isolated star connected load or delta unbalanced delta connected load. And now, if you want to go for typically like for voltage regulation, this again we have to analyze here. So, after load balancing and power factor correction to unity, the balanced star connected load G equal to GY may be considered equivalent to per phase circuit as figure shown here in F, and to maintain the load terminal voltage to be the same as the AC terminal ZVR 0 voltage regulation, another balanced star network compensator may be used. So, we already got GY which is equivalent to per phase delta connected balance load, and we are putting for voltage regulation another substance, so that this voltage equivalent to the source voltage like also. So, the additional susceptance of the compensator BCV for ZVR at load terminal is estimated as follows. So, load terminal voltage V must be the same as the AC voltage, which we already done in single phase, Vs equal to magnitude VL, and this we can find out this typically VL in terms of Vs and parameters of the compensator and parameter of the load and line, and solving this above equation, susceptance of this can be found out in the same manner as we did Xs plus minus under root Xx square minus A bracket 2 Rs Gy plus A Gy square, and then divide by A, where A is nothing but the magnitude of the impedance of the source Rs square plus. So, by connecting 3 phase equal value susceptances of the compensator, each value of BCV in star connection across the load terminal, and its terminal voltage VL is maintained same as the AC mons voltage, and Vs resulting in a 0 voltage regulation like also. With this, we will like to conclude this today lecture. So, what we covered here, passive compensator typically for single phase, for power factor correction at load terminal, power factor correction at substation, and then the voltage regulation typically of 0 voltage regulation at the load terminal for single phase load. Then we have derived the relation for 3 phase 3 wire system, which may be a star connected unbalanced load and delta connected unbalanced load, which converted equivalent to a delta connected unbalanced load. We first compensated the power factor of individual line to line, then we converted providing the load balancing, and after providing load balancing and power factor correction, we got the compensator design for unity power factor, which then this network of delta connected we converted to equivalent to a star connected equivalent admittance, and from star connected equivalent per phase we are able to get again the 0 voltage regulation conditions like it for 3 phase 3 wire system. So, with this we would like to conclude this lecture, and thank you very much.